In this question, we're asked which statement or statements supports or support the delocalized model for the structure of benzene. So first, we should establish exactly what the delocalized model for the structure of benzene is, and that's this one that we draw with the hexagon with the circle inside of it. And the alternative structure is Kekule structure, which has alternating double bonds in 1, 3, 5 positions. So we've been given these three statements. We need to assess which ones support the model, the delocalized model for the structure of benzene. So number one is all carbon-carbon bonds have the same length. And if we think about the delocalized versus the Kekule structure, this delocalized system above and below the plane of the carbon-carbon bonds is supported by all carbon bonds being the same length. In Kekule structure, you have alternating bonds between short for the double bonds and long for the single bonds. And in the delocalized model, we'd expect all 6 carbon-carbon bonds to be the same length, because that delocalized cloud is contributed to and shared equally by the 6 carbons. Number 2 is that the enthalpy change of hydrogenation of benzene is less exothermic than expected. Well, this enthalpy change of hydrogenation is where we add 3 H2s to the double bonds in the 2 systems to turn them into cyclohexane. And it's saying that this is less exothermic than expected. If we think about exo versus endothermic processes, bond making is exothermic and bond breaking is endothermic. So we have the same molecule as the product for these 2 reactions, which means that the same bonds have been made. But if the overall enthalpy change of hydrogenation for the delocalized structure, that's going to be less exothermic than for Kekule's structure because of the stability offered by the delocalized system. The bond breaking, which is the endothermic process, is going to require more energy. So statement 2 also supports the delocalized model for the structure of benzene. Number 3, bromine reacts with benzene less readily than with cyclohexene. So cyclohexene isn't the Kekule structure, instead it's just cyclohexane with 1 double bond. And the reason for benzene reacting less readily than cyclohexene is because of the stability offered by the ring. In Kekule's structure, you would expect it to react with bromine equally as well as in cyclohexene. The double bond is going to react with bromine in exactly the same way because the double bond is localized to this carbon-carbon bond. In the delocalized system, benzene's more stable, so it's less likely to react with the same electrophile. So this also supports the delocalized structure of benzene. So our answers 1, 2, and 3 all support the delocalized model for the structure of benzene. Our answer here is going to be A.